We're going to run through an example of large-scale dynamic simulation with MATLAB. So when we talk about dynamic simulation, we're talking about differential equations such as this one, where we have a differential expression. And this is just a first-order linear system, and it's going to look something like this. Okay, so y of t versus time. We're going to have just an exponential decay to a value of 1. Okay, and we can simulate this numerically instead of having to solve it analytically, and we're going to do that with MATLAB. So first of all, let's just go ahead and create some MATLAB functions here. We're going to come into a new folder. Okay, let's just create a new folder on our desktop. Okay, and then open up MATLAB, and we'll go and navigate to that folder, make sure we're in the right run directory. We'll create a file that's going to be our model file that's going to return our differential term. So we need to rearrange this equation into something that looks like dy dt equals, and then 1 over tau times negative y plus 1. Okay, so we're going to return from this function this right-hand side of the equation, and on our left-hand side is always the differential term. Okay, so this is called a semi-explicit form, so sometimes you just need to rearrange the equation slightly just to get them into this form right here. So first of all, I'm going to change my directory to the desktop one. Okay, so I'm going to come to desktop, select that folder, and then come to new, and we'll go ahead and create a new script. Okay, right there at the top. And this one we're going to use to simulate our function. Okay, so I just like to do clear all, close all, and CLC, which clears the screen. Those are the first three things I typically put at the top of a lot of my functions. And then I'm going to save this as, let me just save this as main.m, just so I know which one I need to run, because I'm going to have a couple other functions in this folder as well. So I want to just set up y0 is going to be equal to 0. That's my initial condition. And I need to do some time points. I'm going to do linspace, the linearly spaced values between 0 and 20, and I'll do 100 of those. Okay, and then I'm going to calculate my response y, which is going to be ODE15S. This is for stiff systems. And I put my model name right here in quotes. That's one way to do it. And then time and the initial condition. Okay, so I can do this. These are the 3 lines that are required to simulate this. If I just run it right now and then come over to MATLAB. Okay, so let's see. I've got some workspace here. I can see that my time values are just going from 0 to 20, and there are 100 of those values, and then I have y0 is 0. So now I need to create this model function as well, and so I'm going to create a new function that I'm just going to call function, and then dy dt equals, I need to have this the same name as the file name, model.m. And then I'm going to do t comma y, and then within this function I'm going to put dy dt equals, and then 1 divided by tau times 1, I'll do y, negative y plus 1. Okay, so that's my very first differential equation, and I need to define my tau value. I'll just say tau equals 10. Put the semicolons there to suppress output, and then that's it. Okay, so this is the end of my function, and I can save it, and it's going to say with a control S model.m. Okay, so there's my function, and there's my main file, and then at the very end, let's just go ahead and plot the results, t comma y. Okay, so I'm going to run it now, expecting that there's probably going to be an error. Okay, so let's see. That doesn't look quite right. Let's go back to our model here and see what's going on. Okay, so I had tau of 10. That's right. Oh, you know what? Tau. There's something not quite right with this. It didn't quite give me the answer I was expecting. So let's just go ahead and debug this, see if we can figure this out. I have, okay, these three. Oh, you know what? It returns actually the first. Let me just print display y. I'm just plotting t versus t there. And I need to have another output. Okay, so it says t comma y, and let's see if that is going to help. Okay, let's see. I did something not quite right here. Y comma t. Okay. Okay, so I'm obviously not doing something quite right here. Let me see if I can. Oh, I need to do this in brackets here. Okay, t comma y. Okay, so it's just syntax stuff, and then you'll get the right answer. Okay, and what we're trying to do here is approximate. Let's try to approximate a step function. So I'm going to plot as well. I'm going to plot 0, 10, so it's going to step right at 10, and then go up to 20. I'm going to do 0, 0, 1, 1. Okay, so I'm just going to have a step function there, and let's do that as a black line with line width equals 3. Okay, and let's do this as a red dashed line with a line width of 2. Okay, so I'm going to run this again, and let's see if I need a comma here instead. Okay, and let's see, line width, undefined variable, function or variable, line width. Oh, you know what? I need to do this in quotes as well. There we go. So just debugging it, you can see the errors there. And this is pretty common, at least for me, going through this, as I write it and then see a bug and then fix it, and then move on. I'm going to do a hold on here. So it holds on to the first one before plotting the second one. You can see the approximation there. So what we're going to do now is just increase the number of differential equations now to try to approximate this step function. And the way I'm going to do that is, okay, so we have some additional equations that we're going to have. This is our y1, and then we're going to have some more tau values with yi, okay, negative yi plus yi minus 1. Okay, and we're going to redefine our tau now to be 10 minus the total number of i's. So n is going to be, we're going to start off with something like 5, and then maybe go to 100, and then 1,000 differential equations that we're going to try to solve, and they're all going to be of this form right here. So let's go and move this over to the side, and then we'll try to set this up in our MATLAB model file. So I need an input here, an n input, because my tau is going to be dependent on that n. And then I have, the first one is going to be dy dt, and that's going to be y1. But then I need a for loop here for I equals 2 to n. I'm going to have some more differential equations. I can copy this one and then just index it with I. So I'm going to create a vector of return values dy dt. that's going to be a function of these yi values and the yi minus 1 values as well. Okay, and then I can end this, and you can leave off this comma. That's kind of an old convention right there. Okay, and then the last thing that I need to do is just make this into a column vector. Okay, like that. Just convert it from a row vector to a column vector, and then end. Okay, I'm going to save that. So now I have this additional input argument right here, this n value. I need to change how I call ODE15s to an anonymous function. So I'm going to put an @ sign there. And the original inputs, which are t and y. And then my model is really a function of t, y, and n. Okay, so this is how I convert this to have an input argument like n, and that's going to be the number of differential equations that we're going to be solving. The other thing is, I think this is going to be converting back to y if you have more than one state that is returned. So let's try this for 5, and let's go ahead and simulate this now. Okay, so it's going to run, and there's going to be an error somewhere, so let's go ahead and fix it. Index exceeds matrix dimension. So one thing that we forgot is on this, if you select this right here, it'll go right to the line where it is broken. And one thing I just realized we forgot to do is change the initial conditions. Okay, and that's going to be just equal to zeros of size n. So let's go ahead and put n at the top, and then we'll define our initial condition. All of our y values, yi values are going to be 0 initially. So let's run it again. Okay, so let's see. Initial conditions vector is 25. Okay. Oh, you know what? That should be a. Let me make this a n by 1. Okay, because it returned a zeros. It's a 5 by 5 matrix instead of a. And you can see that right here. If you double click on this y naught value right here, you'll see that when I did the zeros command, if you just have one input argument, then it makes it a 5 by 5 matrix. Okay, so let's try this again. Okay, so invalid second data argument. Okay, so let's look at our y value now. Y is going to be a structure, and I'm going to have y dot x. That are going to be my times, and y dot y, which are going to be all of the states. Okay, so let's just do this as solution, and then y dot, or solution dot y instead. Okay, let's see. Vectors must be the same length. I'll do solution dot x and solution dot y. Let's see if that works. Okay, so there are my differential equations that are solved. These are just 5 differential equations, and you can see the last one, which is this final red line right here. It's starting to approximate this step function just a little bit better. Let's go ahead and increase this to 10, for example, and just see how this does. Okay, so there's 10, and there's all the differential states as they're calculated. You can see this wave of is propagated down, and you can see the very last one right here is approximating that better. Let's go up to 100 now. Okay, we'll go up to 100, and we can see it's starting to approximate this better. We're just going to take the very last line here as the approximation of this function, and then if we go up to 1,000, for example, it's going to take just a little bit longer, but we'll get a solution just a little bit. We're inputting, now we're doing 1,000 differential equations, and we'll see the result. Okay, so here the very last one is starting to approximate that step function better. Okay, so that's how you approximate these higher order differential equations in MATLAB, I'll show you just one extra thing here that's kind of nice. Okay, so if you do it in Laplace domain, something like this, you define your S as a transfer function, and then you can do a 100 differential equations this way as well, where we would have 10 divided by this would be 100. Okay, n is equal to 100. Okay, so that's going to be 0.1 times s plus 1 to the 100th. Okay, so this is just it in Laplace domain. And then let's do our delay function as well. Okay, again in Laplace, and then we'll do a figure. Okay, and actually let me get that figure back again because we're going to need it right here. And then we're going to do a step on our, let's do it on the delay first of all. Okay, so that's just going to show the delay on our plot. Okay, it's a little bit slow, but hopefully it'll show up. Okay, so there's our step, and then we'll also step our 100 states as well, and then see, I gotta do the hold on, and then let's step our GD value again just so we can see how they compare. Okay, so you can see the comparison of doing the 100 differential states we just did in Laplace domain instead, and use MATLAB to simulate that. Okay, so let's go back to where we started and just kind of summarize what we've done and some of the things that are interesting about this. We have a comparison as you go up in the number of differential equations. So we were thinking large-scale systems that have maybe 3,000 differential equations, and we want to be able to simulate those. MATLAB ODE15S is actually pretty good. It beats the SciPy ODEINT. You can see the scaling here for the ODEINT and the scaling for the ODE15S. Now there's another option as well. One package that I'm working on is this APMonitor package, and you can see the simulation times here in black, almost linear scaling with number of differential equations. One thing I will mention is that there is a compile time. The models have to compile, and so you have this difference in the total amount of time versus the solve time. But once they're compiled, the solve time is very fast in the APMonitor modeling language. Okay, so that's the tutorial on simulating large-scale dynamic systems. With MATLAB, we started off with one differential equation and then went up to 5, 100, 1,000. You can go up even higher with this and just kind of test the amount of time that it would take for the solver to find an answer.